we present a new robot evaluation and benchmarking framework called RoCUS. Existing robot evaluations use hand-picked scenarios and focus mostly on task completion. A developer may construct several obstacle configurations and evaluate the robot's success rate and planning time. This process of hand-designing scenarios risks missing important test cases. Further, this is time-consuming and does not give a comprehensive picture of robot behavior, such as tendency to collide with obstacles. RoCUS automatically generates scenarios to evaluate a particular behavior. A straightforward alternative is to roll out controller trajectories on n random scenarios and choose the top k representative ones. However, when n is too small, we may not find good examples. When n is too large, all of the top k samples are concentrated on the global maximum, which doesn't give insight into the general expected behavior. RoCUS solves this trade-off in a principled way. It generates representative and diverse samples by jointly considering the behavior saliency and scenario distribution via a posterior inference framework. We also introduce a suite of behaviors that focuses not only on task completion, but also on orthogonal quality factors such as obstacle clearance and motion legibility. We analyze two domains. In 2D navigation, the robot needs to move to a target while avoiding obstacles. We consider three controllers: an RRT planner, a dynamical system, and an imitation learning model. We sample trajectories with minimal straight-line deviation plotted as orange curves against random trajectories in blue. We see diagonal symmetry for RRT and the DS stemming from their mathematical formulations. However, the IL samples are asymmetric due to the stochasticity in training deep models. Second, a 7 degree of freedom arm must reach a target under a T-shaped divider. We use deep RL as well as the previous RRT and DS algorithms. We find target locations for RRT and RL that lead to minimal end effector travel distance. While RL target locations are balanced, the RRT ones are mostly on the left side. An analysis of the trajectories indicates that there is a straight line joint space connection from the initial pose to some locations on the left, but no such straight line connections on the right. Indeed, when we evaluate the DS with minimal final distance from the end effector to the target, all of the locations are on the left as well. Thus, we conclude that the asymmetric robot structure results in this configuration space being much less congested with obstacles on the left side than the right. This insight helps us improve the DS controller by informing us that we need to add more obstacle clearance on the end effector. This change greatly improves its performance for right side targets.